Hello everyone. Last video in our thermodynamics series is on Gibbs free energy, or just free energy. And actually Gibbs free energy is represented by the letter delta H, excuse me, delta G. Boy, that was terrible. Delta G. So we have delta H, which is enthalpy. We have delta S, which is entropy. And now we have delta G, which is Gibbs free energy, okay, or just free energy. The whole idea behind free energy is that the calculations we performed in the previous section would be simpler if we didn't have to separate the calculated entropy changes in the surroundings of the system. So now we have this whole idea behind this free energy, okay? Now, the new thermodynamic function was defined by Willard Gibbs. Gibbs free energy was given the symbol as G. And here he said this. So the free energy of the system is equal to the negative temperature times the change in entropy of the universe. Okay? So now check this out. The actual definition of Gibbs free energy is actually somewhat cryptic, and it's hard for me to find it. But it's the amount of free energy to do something. It's the amount of energy to get something done. Okay? So this equation states that a decrease in Gibbs free energy of a system is a characteristic of a spontaneous or product-favored reaction at constant pressure and temperature. So I'm going to tell you right now, we're looking for a negative delta G. That's what you want. For a product to work on its own, you need a negative delta G. You want negative delta G, okay, in order to make that work, okay? So let's look into this a little bit deeper. So here we go. We have this equation right here, and actually this is everything, okay? So when we have this equation, this delta G standard is equal to delta H of the system minus delta T delta S, okay? So we need to really, this is the Gibbs free energy equation. Gibbs free energy equation. You need this equation, okay? Now that we've discussed not only delta H but delta S, and this is a temperature dependent thing, you'll notice, because temperature is mentioned in Kelvin, of course, because this is joules per kmol. Okay, so you need Kelvin. This, in order for a reaction to be spontaneous, another way to say that is for a reaction to be product favored is to have delta G be negative. You want delta G be negative. So, in order to look at this, take a look at this one right here. Delta G is negative for product favored reactions, since product favored reactions say that delta S is positive and the temperature must be less than 0. So if you check this out, you need, okay, there's a better way to describe this. Okay, so let me go this way. Okay, so what I want to do is this, and I think it's coming up. I got something in the back of my mind, but I'll get to that in a second. Okay, so anyway, this one is for a product to be favored, thermodynamically favorable. You need delta G to be negative, so the delta G of the system, so the correct answer is B. Okay, moving forward. Sorry for stumbling there. So now let's talk about Gibbs free energy changes. So now when we talk about delta G for the system, again, we're going to talk about things in their standard states. And you're going to see an equation you've seen before. And that equation's right there. Okay, right here. So you've seen that where the sum of the, the delta G's, excuse me, times the delta G's, which again, you got to look those up in a book somewhere, or they're going to be given, times their moles, minus the same thing to the reactants. So products minus reactants. Third time you've seen this equation, really simple to work, okay? And I don't think there's anything new here. Delta G values for elements in their standard states were 0, so we're back to 0. So delta G formation, standard formation for elements, and delta H standard formation are both for elements are both 0, but not delta S. Okay, so the standard Gibbs free energy formation for elements, so it looks like it's 2 and 3. Okay, so it looks like the answer is D. Okay. They're both elements in their standard states. Okay. Okay, what do you think here? Correct answer is C. Okay, they're in their standard states. Again, remember, standard states is 25 degrees Celsius and 1 atmosphere. Okay. Now, if you take a look at this, this is just using the sigma. Okay. So when we take a look at this, this is the information here, and this is the calculation here. So they plug those numbers in over into here, okay, this slide. So again, you can go back and forth and check that out. Okay. Again, same type of problem. Here's a second example. Those are the numbers down here. Let me just move that up. And the calculation is right here. And again, pause where you need to. Let me just move this up here. There we go. And notice we're at standard states, at least the standard temperature. Okay. Okay. Check out these. And again, I think these are all pretty standard here. No pun intended. Okay, that's that. Move this. So delta G at 25 degrees Celsius. Again, they should state that. And here we go. Pause where you need to. Okay, let's go back to Gibbs free energy equation, okay? Because this is a temperature-driven thing. So take a look at this, all right? If we have the first example where we know delta H and delta S, take a look at this, okay? So we have this equation as written, okay? I want to know, is this reaction spontaneous? Will this reaction run on its own? It all depends on the interplay between delta H and delta S at certain temperatures to give us a negative delta G. So if you take a look here, is it listed temperature? I didn't see. Okay, it says standard, so it must be at 25 degrees Celsius. So 25 degrees Celsius, our delta H is negative 1410, okay, minus 25 degrees Celsius, which is 298 K, times delta S, and says delta S is negative 267. Now, at these temperatures, okay, you can calculate whether delta G is positive or negative, okay? When we see this, we can say that this 1410, by the way, guys, I just apologize, that's 0.267 because that's kilojoules per kmol, okay? So 0.267. So when you actually multiply here, and I want to do this problem, I don't know if they're going to go through it. I haven't looked ahead. But if you take negative 1410, and I'm sorry, let's go 298. Let's get that term resolved. Times 0.267. This term is about 80. So 1410 plus 80, because the negative and negative cancel, gives you a negative delta G, and that's good. That means this process is spontaneous. And I know that ethane, when reacted with oxygen with a little bit of a spark, will definitely pump out awesome stuff, okay, or it's H2O and CO2. Okay? Now, again, these things are temperature dependent. Now, if we take a look at this here, let's see, did they do it for us? Okay, this is just the same thing, okay? So check this out. Calculate the standard free entropy of reaction at 298 K. Okay, we get the answer of 1331, excuse me. They converted everything in joules. I went kilojoules. It's fine. They went back to joules then. It doesn't really matter, okay, how you do that. All right. So that's that. I'm looking for something very specific. Okay, let's try this one, okay? So we're at 50 degrees Celsius. By the time you plug in delta H and delta S, again, I think you'll find that this is quite easy to plug into these numbers, but actually the concept has more implications. Same type of thing. They give you the equation here. They're asking, they give you everything you need. Answer. Okay, now, the effective temperature, this is what I was looking for, on the reaction direction, okay? So, as I mentioned, with the delta G is equal to delta H minus T delta S, that negative T delta S, this is temperature dependent. So when we have this, we need to look at these examples here with this equation in mind, the delta G, or the Gibbs free equation energy, okay? So now when we see this reaction of freezing water, we know that's temperature dependent. So we know that liquid going to a solid, do they give us a temperature? They don't, but at what temperatures, there we go, they're asking us for it, will this reaction be thermodynamically favorable? Well, we obviously know it's cold temperatures, okay? So let's say if we plug 25 in here, that's 298 times whatever delta S is, and if this comes out positive, then this reaction is a no-go at 25 degrees Celsius. Okay? Now, when I plug in 273 or lower, then this reaction will come out to be a, let me erase, this reaction will come out to be a negative delta G. So again, temperature dependent, and this reaction works because delta G is negative. Okay? Now, here's another example, the combustion of gasoline. Okay? So delta H says it's releasing energy. Excuse me, delta H is negative, delta S is positive. Just take a look at this. So if this is negative and this is positive, delta G has to be negative. It has to be negative, okay? As a matter of fact, I believe it is thermodynamically favorable at all temperatures. It doesn't matter what you plug into here, this will always come out to be negative because this is negative and this is positive. I believe there's a chart coming up on this. But whenever delta H is negative and delta S is positive, those are favorable things. You want delta H to be negative. Spontaneous processes tend to be exothermic. And spontaneous processes tend to have increasing entropy. So that's good. That's the best situation, okay, to get delta G to be negative. Here's another example, photosynthesis, okay? When you take a look at this reaction right here, if we take a look at this one, we have now delta H is positive, before it wasn't, and this one's negative, okay? So is photosynthesis spontaneous? Well, you have to take a look here. So if this term is large, then this one has to be even larger in order for this reaction to work because it's negative T delta S. That negative is going to play a role here. Okay, so it turns out that we need a large delta S or high temperatures. So the answer is this reaction is unfavorable. Okay, so high temperatures. Typically, plants don't function at around 10,000 degrees Celsius. So plants need energy from the sun in order to do this. So guys, the way this reaction is written in this direction is non-spontaneous whenever you have a positive-negative combination. Let's go back. This equation was very good when it was negative-positive. Okay? But when you reverse it, it's not spontaneous. No matter what you plug into this temperature, this reaction will never produce a negative delta G. Since negative delta G is never produced, this reaction, as done in forward, does not work. It's actually more favorable this way. Okay? It makes more sense to react and burn this stuff with this stuff to create these things over here. So the reaction, let's go back to the answer. The reaction is favorable in the opposite direction. Okay? Why is this not favorable? You need a continuous input of energy. Okay? Let's look at this example. So now check this out. Okay? It's all about the numbers. If you have a positive, so let's go here. If you have a positive and a positive, okay? This is the mistake I just made. Yes, I did make a mistake. I know it's not normal. But anyway, in this one, now you have a positive delta H. So that's already leading to a positive delta G. I don't like that. I don't want delta H to be positive. I want this one to be negative, okay? I want this one to be exothermic. This one, however, is positive, so that's cool. But here's the thing. I need this term, let me erase here. I need this term here to be large to mask this one. Why? Because it has the negative. And temperatures are never going to be positive because they're Kelvin temperatures. Okay, they're Kelvin temperatures. So even if this is small, no matter what this is, I need high temperatures. I need temperatures in order for this guy to cook and make this thing work. And you notice this is favorable at only high temperatures when the negative term is greater than the positive delta H term. So I'm just playing off the math here, guys. Again, we're always looking for a negative delta G. Here's a beautiful, beautiful chart. Okay? Give the sign of delta G. Okay, let's see if we can do this. Okay. The sign of delta G. When delta H is positive and delta S is negative, at all temperatures, delta G will be positive. That's not good. Okay? That's not good. However, okay, that's the worst case scenario. In other words, this is the one where best if reaction is reversed. Okay, reversed. That way it'll work. That's the worst case scenario. It's funny they started off with that. Next, let's take a look at this one, the bottom one. Now let's go down here. So now I have a negative. Ooh, that's good, because negative things, we want delta G to be negative. This one's positive. Yeah, that's spontaneous at all temperatures. Whoopsie. Negative delta G, that's spontaneous at all temperatures, no matter what. That's the best case scenario. The other two in the middle are temperature dependent. See if you can figure out before I get to it. So let's take a look at this one. If this is positive and this is positive, then what do I need? At high temperatures, that means this term is really going way up. Delta G is going to be negative. That's good. Negative delta G. Where this one has to be positive delta G. It's not really good. So when I have positive, positive, it's high temperatures are good. When I have negative, negative, low temperatures are good. We've got the negative delta G here, and this one's a positive delta G here. Okay, so this one's the good one when it's negative, negative. Okay? Again, why? Because if I have a negative here, again, just do the math. If I have a negative here, that's good. If I have a negative here, that makes this whole term positive because of the negative in front. So I got to have low here to make this mask this. And there's the answers. Okay? Bunch of problems and I'll be done. Okay? So I'll go through these real quick. I know the video's been long. That's C. That's B. Pause where you need to. A. Again, if you want to discuss these in class, we can. B. Get Gibbs free equation in your head. Delta G equals delta H minus T delta S. Okay? All right. I'm going to stop there. We'll cover all the rest later. That's enough. Okay? All right. I'll see you guys in class. If you have questions, email me.